So you want to build a self-driving lab. How do you do it? What are the first steps? Uh, so often it's kind of like looking over the high dive, dozens of feet down, and you sit there and you don't want to get too close to the edge, but just enough that you can kind of see the bottom and really that sounds clear. Who here has gone off of a high dive before? Okay. You remember what it was like the first time you went off?
Remember, I was like scared, like very scared.
Okay, yeah. Your body's triggering all these sensations like danger, danger, don't do this, stay away from them. But then you did. And I think a lot of times when we see this world of self-driving labs where we've got AI and automation, things that we haven't been classically trained on, we're trying to intersect that with the latest and greatest materials, chemical discoveries, it can be pretty daunting. So I'm going to walk through everything, try to encapsulate a lot of what it takes to build that, not so that you think, oh, that's easy, I can do that, but it's less uncertain. You can see some of the videos I'm about to show you and you can say like, oh, I have a gist. I kind of know how they went about that, how much it costs, what kind of personnel would be required. And I know kind of where I'd want to fit in that ecosystem. So perhaps some of you have seen this montage. But this is really the AC's montage of cool self-driving labs that have been built. And we see SCARA-based arms moving all over. We see these high-pressure flow systems. We see your fun 6-axis robotic arms, picking things up, moving things around. We see dozens of tubing all connected to different valves and a fume hood. And then we have the mobile robot chemist that goes around the laboratory and acts like a human might in performing experiments. Now, this is one that I think just really takes the cake here. We have a 2-arm robot uncapping a vial and then transferring that to a robot arm on wheels, which will then pick up the samples, place it in, and then it's going to painstakingly move to the other side of the lab. This is sped up, by the way, like significantly sped up. And it's going to take it to this powder X-ray diffraction machine, which is used to characterize solid state materials and the crystal structure. Right now, what it's doing on the side here was finding its position relative to the table, and then it opens the door slowly on each side. It moves a little bit closer, and then it does this calibration again, touching all sides of this cube, and then it grabs the sample, and it loads the track. And places it inside. And let's not forget that the doors are still open. So we recalibrate and sweep that. We can close the doors. Now, this is from Andy Cooper's lab in Liverpool, and it's really impressive, frankly. This is one of the only systems like this and videos that you'll see at this level of taking a kind of full-scale laboratory and showing this automated workflow throughout it all. And with this, I pulled him off to the side at the end and I said, okay, how many months or years did this take to set up across how many people? And the answer was an entire PhD student's time at university. Granted, a year of that was COVID, and they have slightly shorter PhDs than what you might find in North America, but still, it's that. Then I asked this follow-up question: how much time and effort would it take to replicate this in another lab? And the answer was maybe about half the time, maybe less. But that's still very significant. It's like if you took the same personnel that built this and you plop them into let's say Toronto, and you gave them this lab, and it's like, okay, time to recreate this, ignoring the cost of like an XRD machine or like some of these specialized characterization pieces, probably on the order of $1 million and several years of time to set up. So how do we move from where we're at to closer to workflows like this? And what makes sense to that? So I'm going to walk through a few things. I'm going to walk through the tools that are here in the self-driving lab ecosystem, hardware and software. Those are all tools, and there's no way to completely isolate any of these categories I'm going to talk about, but I've done my absolute best to section them in a way that follows a linear set of slides and presentation. So we'll start out with just what is a self-driving lab? It's a closed loop discovery machine system. So we initialize some starting campaign, some starting set of conditions. We design or decide or choose what experiment we're going to run. We run the experiment, synthesis, these are composition, processing, parameters, synthesis pathways, then we test it. Some measure of performance. And we go through the loop again and again until we reach some stopping condition, which, to be frank, usually means you graduate or your grant runs out of funding or you have to go to the state. So we conclude and then we're ready to kind of set up new campaigns. And self-driving lab combines AI and automation. Now I know some of this might just be like, okay, I've seen this 20 times already this summer. Oh, something. We'll get there. Automation and AI each have a specific purpose in this closed loop discovery. For automation, it's to minimize the burden of experiments primarily. So you'll reduce the number of tedious manual steps. You'll increase the reliability, the repeatability, and the replicability of these. And you'll increase your speed and throughput. This will save researchers time and allow them to spend their time on kind of higher cognitive tasks. It's part of that, as well as having more precise data, hopefully. And then we have AI, which maximizes the value of those experiments that come from the automation. So we reduce the number of required experiments to reach the goal. We choose experiments with the largest information gain. So the information that you gain relative to the cost it took to gain that information. And we often find ourselves predicting properties, quantifying uncertainty, and coming up with really fancy algorithms of how to make a decision. And fully self-driving labs are like fully self-driving cars. Most of the time, they're just not really there yet. And so in the space of self-driving cars, we often talk about levels of automation, levels 0 through 5. So if we do kind of a similar exercise with self-driving laboratories, if we're running manual experiments and it's a human making all the decisions and being the orchestrator, it's level 0. Once we get into automating individual tasks, your synthesis module is automated, or you have this piece of characterization equipment and you load the sample and press go and it's done. Things like that. We get into level 1 style and in terms of the AI and decision making, it could be kind of like one-step processes. You build a model and you make a prediction and then you run one experiment, and that's for the end of the loop. Once we get into automating entire workflows and running multiple iterations, we start to hit levels 3 or 4. And the really kind of intense, awesome lab of the future is we have the full lab scale automation with lots of different equipment, very high flexibility in terms of what kind of workflows can be run on that equipment. And we have our actual campaigns and our targets and our goals being guided by AI. So oftentimes with this, we're thinking, okay, the human comes in and they decide on the experimental campaign. We could imagine a level 5 where that process is also happening today. So really level 4, I would say right now, that's on my mind of the kind of labs that I'm trying to build actively, and then I'll keep level 5 in mind for down the road. And self-driving labs automate lots of different categories within it. So you can think of it in terms of levels, and you can think of it in terms of the hardware and the software and AI and automation aspects. But then we can also break it down into synthesis, characterization, sample transfer, and experiment planning, where experiment planning involves decision making and orchestrating workflows. So to go from a fully manual workflow with all manual intervention, so lots of X emojis, all the way up to fully autonomous, where we have our synthesis, characterization, sample transfer, and experiment planning emoji. This can give you a sense of the level of automation within. So kind of another way to look at these systems, but with the top one being the goal. I say the goal, but the goal is really to accelerate materials discovery. The idea is that goal, we all think, most of us think, that that's the way to accelerate our discoveries. So we'll go a little bit over the tools and the hardware, and this is a set of guiding principles that you can think about as you're building out your own workflows. So one is considering the tension between reliability and flexibility. So your computer, when you buy it, it comes and it's got integrated circuits, and to you, well, it depends who you are, but most of us, I would say, we get a computer and we kind of consider it this black box, this fully integrated system. Now, of course, there are people who build their own computers and make these nice gaming setups and everything. Maybe that's some of you here. But we go from integrated all the way to fully manual. Integrated is very fast, it's efficient, it is very inflexible. When we go to manual, we can do whatever we think of, essentially. And so looking for some range in there where we look for things that are flexible, they're reconfigurable, and there's no one right solution for any given task. Everything I'm going to talk about is on a case-by-case basis. Here's a guiding principle. Decide what makes the most sense for your current task that you're working on. And a lot of times that involves finding middle paths. So this flexibility, reliability trade-off is one of those things where you can look for a middle path. Another one are these nice little tags called April tags. They're a type of fiducial marker. And what that means is it's something that if you were to take a picture of, it gives you both an ID and a relative location to it. So if I took a picture of everybody in the room and I knew where I was and I knew some settings about the camera, I could try to guess where people were. I could guess that Franz over there is sitting further away than Yusuf over here. And that comes from just some basic calculations of geometry and optics. Now you can do the same with tags like this, where these April tags were designed such that if you take a picture and you know the size of the tag, you can get your XYZ coordinates relative to that tag to the camera. So we go from fully hard-coded paths, something where you say, okay, move in X by 5 millimeters and then follow this path, kind of what you get with most 3D printers. What's your hard-coded path? And then we go something full-blown computer vision. We're recognizing transparent beakers and deciding where exactly to clasp them. There's a middle path there where we can orient ourselves to these local reference frames and then do hard-coded paths within those. So once you know a fixed reference frame, this grid system that you can navigate, then we can navigate with it. So pay attention to those. Another one is considering the reuse of existing hardware. So if you have a needle and you need to clean it, a person might take a piece of cloth and hold it in one hand and then wipe it. And so if we follow, human in the loop, it's just the person doing it. If we do a human-inspired design, that means we're going to try to have a robot arm replace the human, and we have the needle and do some kind of wiping motion there. A very interesting kind of redesign of this was we have somebody that had this syringe on a 3-axis system. And what that meant is they could fix a sponge at the bottom and they could insert this tip and then remove it in a helical fashion, which gives you the same sort of friction and forces that you'd find from taking a cloth to it. And like, we can see something similar with liquid mixing. So pouring a beaker into another one, and then having a magnetic stir bar, for example. Now that adds some complexity if you don't already have a stir bar and a stirring mechanism, and you're having to deal with maybe extracting and inserting these stir bars. If you have a peristaltic pump or some kind of pump, when you aspirate and dispense repeatedly, that takes the form of mixing. So there are lots of creative ways you can use existing hardware, and there are limits to this, but again, case by case, choose what makes sense. And then we have this idea of frugal twins. Many of you have probably heard about digital twins. We're trying to simulate the world. There's this project called the World Avatar with a very ambitious goal of simulating everything on Earth. We've got like the metaverse, things like that. A frugal twin is like a digital twin, but for physical hardware. So, I'm just going to lose my voice. So, okay, so a frugal twin is a low-cost counterpart to a high-cost self-driving lab. So we'll take material science and chemistry examples here. At the far end, very capable in terms of research and also very costly. We have a full-blown Instron machine that can pull apart these metal samples and measure essentially the forces and the strain and the stress as we're pulling these apart. And then we have a essentially metal 3D printer that makes these alloys. And so that's that's one of the systems that I'd say a very big challenge in material science is to have autonomous alloy discovery. Now, if we go down a little bit, we might have an arc melter and basically use that with some small scale mechanical testing equipment, or we use a hardness indenter, which is correlated with strength. Then we can get to here, and a little shout out to JP here, who's building this chocolate 3D printer. And why does this appear on the material science spectrum for this task? Well, because chocolate is a form of metallurgy, just without being an actual metal. And so chocolates share many of the same characteristics. There's an entire science behind chocolate making. You have to get it at the right temperature, the right time. You have all these heating curves. And so it's a very interesting kind of materials phenomenon where you could apply the same algorithms that you do for chocolate as you do for aluminum alloys that would go into spacecrafts. And then we have something that's even a little bit smaller scale. If we wanted to do some color matching of powders. So can we mix some powders that are red, yellow, and blue and try to find the optimal color for it? These are all frugal twins of higher cost systems. Same thing with the chemistry spectrum. We could have a ChemSpeed integrated with HPLC, and then we can go to automated liquid handlers and titration, and then mixing food coloring or some kind of paint. So we see similarities in terms of the objectives and differences in the cost and research capability trade-offs. And I'll just point out, so education, that one I think is kind of obvious for some of these. Low-risk prototyping really comes into play. And then we also get into this concept of multi-fidelity optimization, where if you have a close enough counterpart, you can use that within an algorithm, such as Bayesian optimization, and allow the algorithm to choose whether it's going to sample a low fidelity, so lower cost, but lower research capability, low fidelity point, or a high fidelity point. And that goes back to the concept of information gain. How much information are you gaining from an experiment relative to how much the experiment costs? And don't underestimate the pain of manual equipment and GUIs. So when you're contacting a vendor, for example, or you're deciding what kind of equipment you're going to bring in, think about it as an application programming interface, and preferably something written in Python, preferably something that's open source, and ask for an in-person or virtual demo of it in use. Likewise, for something like sample transfer, Anytime you know that you're trying to get a sample into and out of a piece of equipment, does it have unobstructed access either from the side or from the top? Think about that process and ask for a recording or a video of it. We'll get a little bit more into the software now. And like I mentioned, this is decision making and this is workflow orchestration. So a learning problem, I think machine learning, this comes from the idea of a learning problem. It's fully defined by a data representation, a model, you say like a bucket of models that you get to choose from, and some notion of best. So in terms of data representations, for chemical compounds, we could have text, like smile strings, we could have graphs, and that gets into convolutional neural networks, which were mentioned. We have different fingerprints and physical descriptors. And so these are all ways we can represent the data. We have various models, we have generative models, we have property prediction models that I talked about a little bit. And then we get into a very something that's often used in this space, which is Bayesian optimization and active learning. This idea that you take the existing data you have, leverage that information, make a prediction, as something, bring it back in. And Bayesian optimization is a mathematically very elegant solution, a long history and statistics that has shown to do really well for many chemistry and material science problems, where it works when you only have maybe a few dozen data points, you're starting from scratch, and works well up to thousands of data points. And if you do some really fancy models, you can get it to the tens of thousands and so forth. And there are also many ways you can incorporate models from other places and bring that in as additional contextual information for models. Then we also have reactions. So things start to get a little bit tricky when we're talking about synthesis pathways for these different tests as well. How do you represent that as a set of numbers? And it gets tough. So I mentioned Bayesian optimization a little bit. These optimization tasks are always something of the form: find the set of parameters X that minimizes or maximizes a target property Y, or a set of target properties. And what you see here is the comparison between traditional design of experiments and Bayesian optimization. So we have things like grid search and random search and Latin hypercube and Sobel sampling up top here. And then we have this property that we're trying to minimize, and we have the number of experiments so far. And we see that Bayesian optimization pretty quickly just sort of blowing everything else out of the water. This is a function with 6 parameters, and so you can consider it kind of high dimensional. And that's where we really start to see Bayesian optimization do well compared to other programs. Some other tasks I mentioned, the alloys, say find a set of composition and processing parameters that maximizes aluminum alloy yield strength. We could also say find the set of synthesis pathways that maximizes the binding affinity to HIV protease. So a good HIV drug. Talk a little bit more about workflow orchestration. And this gets into another kind of middle path topic. So when we think orchestration, think orchestra. You have somebody there and they're conducting, and if you've seen a really good orchestra, then they are very dynamically adapting and sort of showing people what to do. There's all these signs and things that you do for indicating these people, these musicians, how they should be playing the sounds they are. And in a self-driving lab, we need to orchestrate interfaces with external resources and public databases. We need to leverage internal data. We need to have hardware-software communication, and we need this kind of AI decision-making piece. So there's sort of the glue that holds everything together to have these workflows progress. Now, human in the loop workflow orchestration is a middle path between fully manual and fully autonomous. Now, to show what I mean for that, imagine a workflow orchestrator, a software-based one, saying, "Excuse me, human, please move sample 1 from the vial capping station to the powder dispensing station." Now, this one thing, having a system like this really changes things where it doesn't mean you have to fully automate everything and have everything run via software. So I'll show an example of this. Here, we're running a Python script that's written with the prefect workflow orchestration package. And we're just saying, okay, we started this run. Now, what this will do is actually trigger a Slack notification to the specified user. It'll say, so please move this sample from the automated capping station to the powder handler. And so we're adding links and we can say, okay, I see that this is the thing I'm looking for. That's the thing it should be moved to. Here's my sample ID. And then you open your workflow run. And this is all cloud hosted, built into the interface. And you enter some information. Okay, what's your username or what's your name? You enter that in. Any comments if you need, you want to flag it for review, and then you hit submit. Notice here it says pausing flow. Well, you probably can't read it, but I'll read it for you. Pausing flow, execution will continue when this flow run is resumed. So if we give it a few more seconds, we'll see that now resumed the flow run. It says sample transfer initiated by SG Baird, and gives our other information. Now, if we go back to our just plain old Python script that was running, we also see that same information. And so what's happened is we've had a software-based pure Python workflow orchestrator trigger a person to carry out a manual step. And then the person with very minimal expertise required and report back to the orchestrator, and it passes the control back. So this is a way where maybe you're not at the full autonomy of robotic laboratories. You don't have 6-axis arms picking up files and placing them elsewhere. But if you start with this, you'll learn a lot about what else you need to do to get there. So you'll see things like, oh, I really need a good way to track my samples because I have to tell a person, pick up, take this sample and move it from here to here. You have to keep track of your equipment. And so my recommendation is start out with a workflow orchestrator like this at the beginning as soon as possible. You can set up some AI algorithms very much quicker than you can hardware usually. You can set up a workflow orchestrator much quicker than you can use full robotic systems. We'll go a little bit into the ecosystem as well. So this involves things like personnel, your budgets, your timelines, and the infrastructure involved with these kinds of labs. And your personnel requirements are a lot like playing Mario Kart. So when you have the player and you have the cart, that configuration essentially decides your skill sets, your speed, your acceleration, your handling, all of that. And I would like to pose a question. Would you rather hire Mario, Baby Peach, or Bowser with these different configurations, ignoring child labor laws and anger management issues? We have Mario, who's kind of jack of all trades here. We've got Baby Peach, really good with handling, can't get very much speed, and then we have kind of the flip with Bowser there. So it kind of becomes this question: what skill sets do you bring in? What skill sets do you have, and are you trying to build as part of a self-trained lab? So we end up with needs for highly multidisciplinary skill sets. Now, this is not a comprehensive list, but oftentimes I'll have somebody come in with a lot of physical science domain knowledge, classically trained chemists. And then certain level of expertise on the robotics, on the computational sciences, data science, which gets into model building and active learning. Software development, everyone in this space is kind of expected to put on a software developer hat, despite having almost zero formal training in software development. And then engineering. The joke, I guess, in chemistry is everyone has to become a plumber to be a chemist. It's like a lab chemist. And what you find is that having these cross-disciplinary teams produces a big language barrier, a language gap. So if we take the extremes of somebody who has a lot of physical science domain knowledge, but essentially no understanding, awareness of the other fields, same for robotics, same for computational science, data science, we end up with a situation that sounds a bit like a joke. A chemist, a roboticist, and a data scientist walk into a bar, and it goes on. And you may as well be speaking like French and Japanese in a lot of these scenarios. You can also think of this in terms of a dot product. So we treated all of these as a dot product. I think it's coming across. What's the result of the dot product? Not very much. And that comes from these communication barriers, not just in terms of the terminology, but the concepts themselves, as well as the overall goals of the research project and the kind of personal interests of the people involved. So how can we build up these sort of weaker spots in our own, our own skill sets, not to make ourselves an expert in everything, which just isn't reasonable, but know just enough that, let's say we're handed a system in this weaker domain of ours. We know how to tweak it. We know the concepts behind it. We know what questions to ask about it. And we all kind of get on the same page. One other thing I want to bring up is this idea of existing standards. So during graduate school, well, maybe a little bit back, I started out as an applied physicist and was so my classical training was applied physics and material science. And in many physics programs, we use the language Mathematica, which is a very, very good symbolic mathematical programming language. It's awesome at that. And it works really well for some kind of like high power computational, but lots of symbolic solutions, characteristic of physics. Now, I was taking a course and it's called Theory of Predictive Modeling. And in this course, we were told you can use whatever programming language you want for these assignments. However, the TAs and all of the worked out solutions or examples will be in Python. Now I thought, I love Mathematica. Mathematica is great. So I did almost the entire course in Mathematica. And what that meant is that no one else in that class could help me. And I couldn't help any of them. Now I learned a lot and it was really fun to actually code in Mathematica. But that aside, when you kind of break a standard, you lose the ability to very seamlessly integrate with the rest of the community. So it's not to say you always have to follow what somebody else has done, but when you adopt existing tools and kind of existing ideologies and the best practices that come along with that, then it can save you a lot of frustration and really streamline your throughput and your output. So if you run some Google searches for awesome self-driving labs, which is this community curated list of self-driving labs and related resources, so review papers and original research articles and lots of tools and other things. That's a good place to go to see what other people have done. And then there's also an accelerated discovery forum. And so this is a forum dedicated to self-driving labs. If you have questions or want to start a discussion about the different tools, like how do I manage the tension between what I build and that infrastructural output versus my actual scientific output when I'm writing publications, and as to as specific as like, okay, I'm dealing with this OpenTrons API and I'm trying to do this one task. Like, how do I go about that? So we'll move on to this next part, and I think many of you are familiar with either the slide or the microcourse because you've stopped by my office and I've grabbed a bunch of items from these bags and then put them all together. Some of you got them a little bit more wrapped up. Some of you had to kind of hold on to them, like these 7 distinct items. But this goes back to the micro courses for the acceleration consortium. And this is the one slide overview, everything about the micro courses. So these are meant to bridge cross-discipline terminology, like I talked about, kind of increase the overall value of that dot product, increase your conceptual understanding, and give you some hands-on experience here. And this flows from an intro course into deeper dives into concepts and then a project-based course. So the first 4 here are fully online and asynchronous. This one is launched. Many of you are registered for it. We have star pupil Serene, who actually completed it already. So well done. And then these ones, expect them to be ready to go within the next 2 months, which might be nearing the end of this time here, but keep an eye out. And first one, you're designing and building a small light mixing demo from scratch that captures a lot of self-learning principles. These next ones, you're writing code that optimizes materials. It's a lot about optimization and then also about database backends. Then we have the robotics. How do you control a linear actuator? How would you control a peristaltic pump, a stepper motor? How would you control an Opentrons or some other automated liquid handler? And then getting a little bit into your fun robotics with 6 degrees of freedom, inverse kinematics, and how to pick up things and place them. And then software development, like I said, we have this insane expectation or need to all be software developers with no formal training most of the time. And then software developers come in and they're like, oh, here are all our best practices, but they know almost nothing about chemistry or material science. And they want us to be convinced of the beauty of these concepts and understanding. And we just say, but I want the code to run and I want it to work. So there's some tension there, and hopefully this will help a little bit with bridging that. My final closing thought to you all. Your next steps. So at the very beginning, I showed the diving board and said, okay, this presentation is about showing what your next steps are. And you're probably sitting here wondering, well, what were my next steps? The answer is it really depends on you, your existing skill sets, and where you want to go. But I would encourage you to look for your intersection of your existing skills, your interests, and your opportunity. So your opportunities during the summer they're really defined by, okay, what group are you working with? Who are your main contacts and resources? What projects have kind of been outlined for you? What equipment's available to you? You have your interests, which most of you talked about at the very beginning here. And then we have, your existing skill sets and kind of like what skills you want to build and what you can leverage already. So I would encourage you to do a few things. One, look up the Awesome Self-Driving Labs repo. Just Google it. Awesome Self-Driving Labs. It should be easy to remember. And then also Google Accelerated Discovery Forum. And both of those should be some of the topics there. And get started. Feel free to post on there with thoughts or topics, and take some time, sit down, think, what's my next step? What am I going to do to get to that goal, that end of summer goal? I'm shooting for. Yeah, that's everybody.
The video that you showed at the beginning with the self-driving lab, that was sped up. It still looked like a normal speed. So a little bit curious, like how much time does that actually save versus having like
Yeah, that's a great question. So I think that I'm very opinionated and biased in absolutely everything I say and all the things I share. So keep that in mind. With that thing, I'm usually not as worried about the time it takes for an iteration. If it's closed loop, what that really means is it reduces the burden on the researcher who's leading or designing the project. Anytime you have a manual step, I picture in my mind, like my foot is just stuck in the mud and I have to keep some level of mental focus and concentration on, I have this manual step, 6 months later, you still have to be managing that and kind of keeping that in mind. And it makes it harder to move on. As soon as you have something that's autonomous and it's robust, you no longer really have to think about it. So in that sense, I see that as a big appeal is you set up an autonomous system and it frees you up to continue to other ones. Now, why not have excuse me, an undergraduate, say transfer the sample from point A to point B? Well, it makes sense a lot of times. That's where human in the loop comes. I would just caution against making the human the orchestrator, because that's really what causes a lot of this burden and allows you to it kind of encourages you to set up everything else manual. As soon as you have a human orchestrator, so many other pieces that you'll find yourself running into so many problems later on and trying to convert to automated solutions on the individual pieces. So people can do the work, but minimize the sort of mental burden and concentration that's needed and get your foot out of the mud. Let set up the automated orchestrator. That's my very biased opinion on the matter.
Do you think that when you showed those graphs of cost versus research capabilities, do you think as we go forward in time, the cost of certain instruments will decrease?
Yeah, I think so. And they'll also get more expensive as we get more performant on things.
Yeah.
So you'll be working on Science Jubilee, right?
Yeah.
And this is a fully open source and relatively low cost system that has been used to sort of push the bounds on just, here's my automated liquid handler to now here I have an automated tool changer that can do liquid handling. And you could mix slurries with an ultrasonic horn, and it opens up a lot of flexibility in terms of the kind of tools that you can have. Now, you'll reach limits at some point. In the end, it's a gantry-based system with XYZ and tools that you can put on it. But that, as we see systems like that continue to evolve, I think we'll see the democratization of science itself and the accessibility of automated solutions really start to, we'll see that barrier get lowered. And that'll show in terms of cost. And we'll see that in the range of people using them. Did that answer your question?
Yeah.
Okay. I'm really good with awkward silence, guys. So I'm gonna wait for one more, and then I think we'll. Okay,
It's not really related, but in the Mario side, we have Mario and Baby browser.
Yeah.
Was the point there to show that Mario is supposed to do?
no, not necessarily. I mean, Mario's pretty great, but the point there was more to think about the kind of skill sets that you need.
Yeah.
If you only had a Mario, you got to think about whether you'd be tackling the most interesting and most impactful research problems. And you'd run into issues with, I'd say, how far you can push the bounds on what you're automating and the sophistication of the kind of algorithms you're using. And so I think maybe part of that is figure out where you're at or, where the people you're interacting with are at and build up the weaker spots just enough to make it easier to communicate and make that communication more.
And I would say with that, technically, all the pro players use the heavyweights, like Bowser.
Okay.
Donkey Kong, those are actually better ones.
Good to know. Okay, I'll keep that in mind for the next time.
It's pretty good too.
Okay, keep that in mind. And I think you guys were interested in doing a Mario Kart. Game. So just really think about software and labs while you're doing Kart next time.
I'm just wondering. So, would in the slide after that, when you mentioned about the translators and whatnot, if you had So what you were saying is if you had like a person who was all three, like not all five, like they know enough for all five categories. They're not an expert in it necessarily, but they know all five, like certain concepts equally and stuff. Would that person serve as like a translator between them?
Yeah,
Uh,
yeah, I think so. And in some ways, it could be argued that someone like that might do well in kind of a like manager role, somebody that can kind of connect the right resources, help people to align on goals. You might even say somebody who really strives for that might be good at trying to make some training content a little bit. Notice the word strives there. But yeah, I think, you know, in some sense, maybe back to Justin's point, maybe you need lots of, you know, people across the board like that. And if you have a diversity in that team and the skill sets, then you're more likely to make it to your goal. Okay, thanks everybody. Thanks for being here. Yeah.